We talked, all right, so we are recording. We talked in our last class about the concept of flux. We talked about surface integrals, and then we talked about how a flux integral is actually a surface integral. And what is flux? Well, with flux, you have a surface, and you are studying the rate of flow passing through the surface. What is the net rate of flow in mass of fluid per unit time? And it's a concept used in many applications. For instance, heat flow is an application. Net charge, Gauss's law, electric flux. So there are many applications coming up with these flux integrals. Now, it turns out that flux integral can actually be helpful in a theorem called Stokes' theorem. So this Stokes' theorem that I'm going to show you is named after the Irish mathematical physicist Sir George Stokes. He lived from 1819 to 1903, professor at Cambridge University. And the theorem you're learning in section 13.7 is named after him. Although it mentions that Stokes' theorem was actually discovered by Scottish physicist Sir William Thomson, known as Lord Kelvin. I'm sure you've probably heard of him. But at any rate, okay. So let us go down here. Stokes' theorem can be regarded as a higher dimensional version of Green's theorem. Now, what's Green's theorem used for? Green's theorem is used to find the work that a vector field does in moving a particle once around a closed path, but the path is in two-dimensional space, an x and a y axis. What if your path is not in two-dimensional space? What if it's in three-dimensional space? Well, this is where Stokes' theorem is helpful. So in the picture here, in figure 1, you have a space curve C in three-dimensional space, okay? And the space curve C encloses in its interior a surface. Now, what's the outward orientation? Remember, outward orientation is critical when we're talking about flux. Well, we have to know what orientation are we talking about, outward or inward orientation. But by default, outward orientation is what's used. So in the picture here, you see in figure 1, you have looks like a little man walking along the space curve. And to the left of him is the surface. To the left of him is the surface as he walks around the space curve. The normal vectors point upward. That's positive orientation. So what Stokes' theorem says is, if you want to define the work that a three-dimensional vector field does in moving a particle once around that closed path in three-dimensional space, you can't use Green's theorem, right? Because Green's theorem's for two-dimensional space. What does Stokes' theorem say? How can you find that work? Well, here it is. It turns out that the work is equal to the flux integral. Okay, that double integral to the right, where you have the dot ds and the s is a bold vector, that's a flux integral. It's a flux integral where the vector field is the curl of the vector field. It's an absolutely amazing theorem, and they prove a special case of it in the textbook. We are going to look at a few examples that deal with Stokes' theorem. We're going to get right to it here because you probably have noticed, how many noticed these problems? There's a lot of pieces to these problems that you're seeing later on here in chapter 13. You have to find parameterizations and so forth of surfaces and all that. I mean, so I think focusing on doing some examples is the best use of our time right now. So let me bring up this example. Now this example here is actually an example. It goes with example 1 in the textbook, but I want you to put it in your notes, formally write it in your notes. So let me give you a moment to copy this example down, and please let me know if you have any questions. Okay, so let's remember our notation. So you have here an expression that stands for work that this vector field does in moving a particle along this path C. Now in this case, because along on the integral you have the closed circle there, that closed circle, so when I say closed circle, I'm talking about this here. That means that we have closed path. Closed path. And indeed, our path is closed. Our curve C is closed because it's the curve of intersection of the plane y plus c equals 2 and the cylinder x squared plus y squared equals 1. So if you take a vertical cylinder with radius 1 and you cut it with this plane, okay, which we can think of as z equals 2 minus pi. Just think of taking a plane, that plane, and it cuts through the cylinder. The cut is going to be the space curve, right? So Green's theorem would not work here because this space curve is not located in the xy plane. It's located in three-dimensional space. Are there any questions so far before I go to the next page? Okay. All right. Oh, just so you see, this is that formula sheet that you have access to under handouts on the final exam. So you're welcome to print this formula sheet out, by the way, as well. But you don't need to. It's there in Blackboard under the handouts folder. Okay, so let's start off with our solution here. Let's start off with a picture. So in the picture, what I have here is the cylinder, and it got cut by the plane y plus c equals 2. Okay, and this actually resembles figure 3 in section 13.7. Here is the cut right here. Here's the cut. And there in red, maybe I'll make it 2-point font so it's a little more. Here's your space curve. Which is the boundary of that cut. And then inside the space curve, you have your surface S, which is obviously a portion of the plane. And the normal vector points up from there. That's positive orientation. Positive orientation. So, okay. Stokes' theorem, remember, Stokes' theorem says, okay, this work here the work that we're looking to find is equal to the flux integral across surface S, where our vector field is the curl of the vector field. But remember, to find a flux integral, I mean, this is a flux integral. Because of the d vector S there, we have to say to ourselves, how are we going to find the flux integral? Well, if we go back to the formula sheet, actually, which is why I have it here, okay, here is the formula to compute flux. Now, the vector field F, okay, we have, instead of the vector field F, we have a vector field F. It's just the curl of the vector field. So this is the formula that we should use. And in order to use the formula, we need to find the cross product of the derivative vectors of your vector function. So, you know, when you see this part here, you have to say, okay, what's my vector function? Maybe let me make that. Hold on here. That's a little bit. Yeah, got to find that. I got to find my vector function that traces out the surface S. Well, the surface S, if you notice here in the picture, it's the surface enclosed by the space curve. And that surface is part of the plane. So that means that, okay, well, since the plane is y plus c equals 2, that means z equals 2 minus y. All let x be x, all let y be y. So it's convenient to let x and y be my parameters. The restriction on x and y is that x squared plus y squared has to be less than or equal to 1. If you take the surface S and project it down into the XY plane, you're going to get this as your region D. So now it's just a matter of applying Stokes' theorem. Are there any questions so far? Who's feeling good so far up to, up to here? Okay, Yeva's all right, good. And Noreen is good, all right. Okay, okay. So given then that we have our vector function of parameters x and y, we can compute the derivative vectors with respect to x and y and take the cross product, because that's what that formula that I'm going to use to compute the flux requires me to do. When I do the cross product of those derivative vectors, I get j plus k. Remember now, when you do the cross product of the derivative vectors, you have to be sure that, I mean, what does that cross product vector give you? It gives you the normal vector to the surface, right? I mean, that's, let's say this the right way. Yeah, it gives you the normal vector to the surface. So, but the normal vector has to point in the right direction. Well, if you look at the picture, okay, and you look here at, there's the normal vector right there. Okay, it clearly points upward. So the components would have to be, well, it's pointing to the right and up. So the coefficient of j would have to be positive. The coefficient of k would have to be positive for the normal vector. And in this case, you get a 1j plus a 1k. So yeah, yep, it works. Now, if you were to do the cross product, if you were to do ry cross rx, okay, you would get negative j minus k. All you do then is just, adjust that so both components are positive. So one vector, when you do a cross product, the vectors, you'll get a normal vector to the surface, but it'll either point outward or inward. If it's pointing inward, just negate it so it points outward from the surface. Okay, so hopefully this is good so far. All right, well, what's the next step now? What's the next step? Well, if we go back to the flux formula here, well, we have to put in our, what is our vector field F? Well, because we're using Stokes' theorem, the vector field F is the curl of F. So we have to find the curl of our vector field. Please let me know if you have any questions, and if not, I will proceed to the next page, of course. Give me a thumbs up when you're ready. Okay, Yeva, very good. Okay, Norina, very good. Christopher, very good. All right, so we have to find the curl of, we have Stokes' theorem, we have to find the curl of our vector field. Well, we know how to find the curl of a vector field. The vector field has components negative y squared, x, and z squared. So we just put those in the bottom line of the curl. And then we have the del operator, or on the second line. Okay, so remember, let me see here, one moment. So the curl you learned back in section 13.5. And let's see here. So this is just the del operator, cross product of the del operator with the vector field. And I work it out, and I get 1 plus 2ik, which has component 0, 0, and 1 plus 2y. I'll let you copy. I'll have to give a shout out to Olivia Newton-John. She was a great singer. She passed away yesterday. But when I grew up, you know, everybody loved her. All right, yeah, Yeva sad too. Yeah. I put it in the recording. I just got that one I got to mention, you know. Yeah, that's right, Simon. That's right. Check out movies like Grease and Xanadu. Great movies. I remember when I was a kid, you know, back then we had like HBO and Showtime. Those were like the we didn't have like other movie. Yeah, you had cable, HBO, and Showtime. And I remember I wanted to see Xanadu, and you know they only had them at certain times. It wasn't like it was like Netflix where you could watch it any time. They were scheduled for certain times. And I remember one time I got up at 6 in the morning to watch Xanadu. So you know, on a Saturday morning, because that's when it was on, you know. So all right, so we have the curl of our vector field. And I hear that, Alexander. Alexander loved Grease. Oh yeah, great movie, great. So we have everything we need now to proceed forward, and let's go ahead and compute the work using the Stokes theorem. So I'm trying to put in some details for you. And it's going to come down then to computing this double integral. I decided, since the region D is a you know, the limits on our parameters x and y, the restriction is x squared plus y squared is less than or equal to 1. That's a circle, a filled in circle. So it makes sense, since the region D is a circle, that we would want to use polar coordinates. Okay, so take a moment to copy. Please let me know if you have any questions. I'll mention while I'm at it that, again, this goes with example 1 in the textbook. Now, the textbook, because the surface comes from the plane z equals 2 minus y, the textbook treats the surface like a graph. And you know, this, like the formulas, I like to use parameterization. I like to parameterize my surface. So I had gotten a vector function r of x and y. But you could treat the surface like a graph, and then you know, the general formula collapses into those formulas where you have graphs of functions, you know, so like z is a function of x, y. You're welcome to do it that way too. They do that in example 1 in the textbook, but I'm doing it using the formula, you know, that always is going to work. Because you can, if you don't have, if z is not a function of x and y, or x is not a function of y and z, or y is not a function of x and z, if you have that kind of situation, like for instance, if you know, if your surface just couldn't be written as a graph, you would have to find the vector function of the parameters that scratches out the surface. So I just prefer to use, I like to use something that always works, you know. But all right, so let's see here. I think we're good. I think if you're good, let's go ahead and proceed on. For this double integral, of course, we do iteration. So the inner integral, you're integrating with respect to r. So that means you hold theta a constant. So sine of theta would be treated like a constant. This is your inner integral. You substitute in 1 and 0. And now you have not a double integral more, but a single integral. And you get the antiderivatives and you're good to go. And it turns out that the answer is going to be pi. That's going to be the amount of work that vector field F does in moving the particle once around its closed path. And so it appears that the net effect of the vector field is to help the particle move around the path. Naturally, to graphically see that, you would have to graph the space curve along with the vector field. And hopefully you would see the net I mean, you would see that that's occurring. Please let me know if you have any questions. This is truly some beautiful mathematics, isn't it? Truly beautiful. Okay, who's feeling good with this example? Okay, Narina's good. Yayla's good. Aura's good. Wonderful. Logan, how are you with this example? Are you good with this? Wonderful. Ashfiha, how about you? How are you with this example? Okay, good, good. All right, well, I do want to do another example with you, but I'm going to have a separate recording for that example. So I'll stop this recording and we'll do another example here. Very good.